he really manages to make that bit equal to my input is quite small, or rather, it's not too big. Namely, he only has an 85% chance of being correct if he does not know that I've used the blue encoding. Okay. So knowing the encoding of the bit is evidently important. And it will be true, it will be important for us that in fact Bob cannot do any better. Even if I let him do anything he wants here, he can output something. And later I'm actually going to tell him, Bob, I've used the blue encoding. And this is not going to help him at all. That the probability that he will be correct is still 85%. Okay. You might wonder, where's this going and why is this important? Let's compare the cases where I have storage and where I have not storage. So again, say I've chosen 0 and the blue encoding, and Bob could store it on some quantum hard drive. So then later, when I tell him, hey Bob, I've chosen the blue encoding, he can perform the blue measurement and get out exactly my bit with probability 1. So with storage, perfect success. Let's look at what happens without storage. So I sent this to Bob. He can do anything he wants, any computation, but he has no quantum storage. So out comes the classical bit. And later I'm going to tell him, hey, I had the blue encoding, and he can perform any measurement or operation that he wants on the classical bit and the fact that I tell him I've chosen the blue encoding. And still, here he has only 85% being correct. So maybe he manages to guess correctly that I have a 0, but sometimes he'll output a 1. So without storage, he cannot do it perfectly. So maybe I should make a remark, because you may have been wondering where do these uncertainty relations come from. Uncertainty relations cannot really apply only to measurements, but they can also apply to encodings. And namely, this is exactly what we're doing here when we talk about the red and the blue encoding. So now that we know what happens with and without storage, of course the obvious question is, what happens if we have some storage? So say we do this many, many times. Sometimes I choose a 0, a 1, at random, and sometimes I'll choose the red, or sometimes I'll choose the blue encoding. I'll send this all to Bob. Bob, like I said, he can do any encoding he wants. He may have some kind of quantum computer. But he only can store, using some noisy storage, k times m of these bits. So k here can be some number, for example, maybe a half, but it can also be greater than 1, so it could also be that he has twice as many channels here as the bits that I sent him. So, like I said, so there is actually some chance that Bob succeeds, even if he does not know the encoding that I've used. So some of these bits over here are equal to the original input. So for example, this one, and that one, and the one down here. But some of them will be incorrect. And in fact, one can show that an uncertainty relation, now not applied to measurements, but to encodings, tells you something about the rate at which Bob has to send information through his storage. But we had just realized that if the rate is too big, namely it's greater than the capacity, or in fact, if we use so many channels, it will in this case tell us that if the rate, which is a half, so this comes from some uncertainty relation, is greater than k times the capacity, then in fact the probability that Bob really manages to guess the entire string goes to 0, as m is large. So he may know some of the bits, but surely there are going to be also some bits that he does not know. So I guess you're all familiar, so it will go, so this here is m, this here is the probability, so as m goes large, this goes to 0. You may ask, how quickly does it go to 0? I don't really want to talk about it. It depends, of course, on what the channel is here and also what this number k is. So it may go a bit quicker, like over here, but also maybe a bit slower. Okay. So now that I've talked about some quantum ingredients that we're using and how they're related to noisy storage, I want to introduce, it's a well-known primitive, a cryptographic building block that will allow us to make this other primitive. But it's going to be much simpler. And it's called 1 out of 2 Oblivious transfer. And the name comes from the following. Namely, Alice has 2 inputs, S0 and S1. So these can be strings of a certain length. Bob has some input C. This is just 1 bit. And it labels which of the two bits Bob actually wants to know. So this, as an idealized box, it should work in the following way. Alice inputs her 2 strings into this box. Bob inputs his choice bit C. And Bob can learn S sub C. So he can learn the bit he wants. The security conditions here mean that Alice can learn nothing about C, so she does not learn which of the 2 bits Bob wants. And at the same time, Bob can learn not more than 1 of the 2 bits. So there's always 1 of the 2 that he is ignorant about. So like I said, these are the conditions. And you may wonder, why is this at all interesting? How does this fit with the previous problem? So let's imagine that we have some function that outputs just 1 bit. The output can be longer, but Bob's input here is just 1 bit. So note that this is we could easily make this from this 1 out of Oblivious transfer. So Alice inputs, her first input is just her own input. And if Bob would have input 0. And the second one is this function applied to her input and Bob's input equal to 1. So she doesn't know, of course, which of the 2 inputs Bob has, but Bob can now retrieve the one that corresponds to his input y. And so the conditions are that, in fact, Bob can learn nothing, Alice can learn nothing about y, so she doesn't know which one Bob has, and Bob can learn nothing more than just S sub y. Okay, thank you. So let's give you a very rough idea about how a protocol for such a thing can now be built from using quantum bits. And I just want to tell you the main 3 steps, which are the following. So first, we're going to generate a very long string, which is shared by Alice and Bob. And it will have the property that Alice knows all of the bits, but Bob only knows some of them, and not too many. Then we'll split the string into 2 parts, and it's possible to do this in such a way that Bob knows one of the 2 parts, but not the other. But he may still know a little bit about the other part. So in the final step, we'll actually shrink the strings down to something much smaller, and this will have the nice property that Bob knows one of them, but he really knows nothing about the other. Okay. So let's start with that. So let me again recap what we're trying to achieve. So what we're trying to do now in the first step of the protocol is to build something that sort of works like the orange box here. So to Alice, it will spit out a long string, x1 to xn. And Bob will get some set I, so this is some subset of the bits from 1 to n, and x sub I, so this is the string x at the positions in the set I. So we want to do this in such a way that Alice does not learn which of the bits Bob knows, and Bob cannot guess the entire string. So he may know something about it, but not too much. So for example, we can